my notes. Okay, is that everyone? Nope. Two more, okay. Okay, so can I start? Is everyone good? Cool. So I'm going to be teaching some combinatorics, and I'm mostly for today going to be working through chapter 1 of a book called Combinatorics by Richardson. Okay, MIT. So we're only going to do like part of chapter 1 because, well, it's a graduate textbook. Okay, so the first thing talks about is what is a combinatoric, what is a formula? What does an answer look like?
A lot of exclamation marks.
No, not a lot of exclamation marks. That's not always true. So here's a question. How many subsets of this set? Is that right there? Well. Okay, anyone know the answer? 2 to the n. Okay, so what can we say about this answer? Okay, this is a good one. Okay, it's simple, it tells you what the growth rate is. Like, this is like as nice an answer as you can get, right? Yeah, pretty much right. Okay, so how about how many permutations of that same set? Anyone? Pretty sure you all know this. N factorial. Well done. Okay, and that's got a lot of the same properties, right? It's a single expression. You have some idea of how quickly it's growing. It's a nice answer. Yes? Okay, let's do something which is a little bit more interesting. Who's familiar with the term derangement? Who has not heard of the term derangement?
I've heard of it.
Okay. And the rest of you are like missing both your hands, or? Okay, I'm going to assume that. So let me define a derangement. Do this here. So derangement is mutation fixed points. Okay. So you're going to arrange the numbers from 1 to n, but you can't put 5 in place 5, 4 in place 4, 2 in place 2, and so on. Okay? If you're familiar with sort of thinking of a permutation as some non-attacking rooks, right? Okay, do we have any answers for D4? Sir? Guys, any answers for D4? 6?
Just a guess.
What's that? Okay. Baron?
6.
6. Okay. Anyone else? Okay, so I think that's right, but you guys can see just by kind of working through the small case that you really don't want to work through many larger cases, do you? Probably not, right? Let's go for a question, I think. Okay, so, well, who's heard of inclusion exclusion? Okay, so you've all heard of inclusion exclusion. Okay, so what we do is we look at, we say, there are n-factorial permutations, right? We all agreed on that, yes? So now, if one is fixed, if one ended up being a fixed point, how many of those permutations would there be? N minus 1 factorial, right? Yes? How many permutations are there where 1 is placed with 1? Just 1, right? Maybe I should... yeah, okay, and there are n people, right? The n ways to have a fixed point. Okay, each of them has n minus 1 factorial, so we just subtract them off and get no derangements ever. Okay, of course that's not right. We also have to add back the times when there are 2 fixed points. Okay, so if there are 2 fixed points, how many ways are there to pick 2 people to be the fixed points? Yeah, so plus n choose 2, and then n minus 2 factorial, right? Okay, then minus n choose 3. Choose 4. Factorial minus dot dot dot, all the way up to n, right? And this is inclusion exclusion. Are you guys comfortable with this? Slower, faster, just the right speed? Okay, everything's perfect, great. Okay, so let's do a little bit of algebra on this. That's n factorial. That's n factorial. That's n factorial over 2. That works out to being n factorial over 3. That works out to being n factorial over 4 factorial, and so on. Right? Okay, and this is n factorial times by 1 minus 1 over 1 factorial plus, okay, and so on. And I'm kind of lying a little bit here, because this is only going to be minus 1 to the n over n factorial, right? This isn't an infinite series, even though I've kind of just went dot dot dot. There is actually a last term. Do you guys want me to put that in? Last term. Okay, it's there if you want it. Okay, now we said that 2 to the n and n factorial were really nice formulas, right? If you get a formula like that, that is sort of the answer, right? No, it's okay, cool. This is a bit less nice, right? Like it's this long alternating series.
It looks a bit like, yeah, it looks like a bit like the Taylor series, series with the exponential function.
Very good. So we're getting into that. But this is a precise formula. It's exactly computable and it's all good. Here's another formula. Well, here is something that it's about. It's approximately n factorial over e. In fact, it's not too hard to show that it's exactly equal to n factorial over e rounded. Okay, so it's the nearest integer to n factorial over e. And now we sort of can ask ourselves, which of these formulas is better? Okay, better is a little subjective, better for what? This shows us a lot better what the asymptotics are, right? Make a random permutation, the probability that you will avoid any fixed point at all is about 1 over e. Okay, and it doesn't depend on the length of the sequence, at least beyond a certain length. That's a little surprising, right? Okay, and this one is exact, but it's uglier, and there's some sort of tension between what constitutes an answer. So here is a slight extension to this. How many fixed points are there with exactly k? So how many permutations are there with exactly k fixed points? Okay, so you say choose the k first? Yeah. Okay, so it turns out there are n choose k times dk, about. Alright? Yes? No? Cool. And let's actually do a little bit of an expansion on this. N factorial. Okay, and dk we said, I'm going to make that an approximate, k factorial over e. So that's equal to and I can write it to the okay. And this is nicely related to something called the Poisson distribution. Okay, so this fraction of that. So your chance of getting k fixed points is 1 over n minus k factorial times e. Unless I made some.
No, k 0.
K is 0, they cancel. Did I? So k 0 it is e to the minus 1. What are those guys?
I think k is. No, and there shouldn't be d in minus k.
Yes, that's it. So in first place, n minus k, that's equal to e, which is n factorial over. Thanks. Okay, so the fraction of the time that you'll actually get k fixed points is about 1 over k factorial. Well, it's e to the minus 1 over k factorial. Integrally. Okay, so here's another question. So, how many 0, 1 matrices of size n by n are there with okay, you guys understand the question?
So maybe it's only if there's
Yeah, matrices, only zeros and ones, mostly zeros, in-bane matrix, 3 ones per row, 3 ones per column. Okay, so if n equals 3, there's just the 1. If n equals 4, right, just the 1. N equals 4 is going to be a bit more complicated. So here is the best known formula. Okay. Squared. Yuck.
What's that sum over?
Sum of alpha plus beta plus gamma, non-negative integers equal to n. That's sum to n. That's all the solutions of that form. Okay. That's really awful.
Yes.
Okay. Now, on the other hand, is that a formula? Is that an answer? Is an answer in an Olympiad? Well, kind of. I mean, if you have that, you can use it to count those things. You can get answers. And if someone comes up with a nicer formula, well, we prefer that. There are, and Stanley says, which will forever be nameless, I don't know what they are, but there are formulas in the literature which are really just, and I'm going to sum across all solutions. Here's another answer to that. Sum all such matrices. Just count them, sure. That's an answer, it's just not a particularly useful one. Okay, it's so yes, welcome to the trade-offs of these things. Now what you'll notice is this last problem with this horrible formula. It's a lot harder than the derangements one, which in turn is a lot harder than the permutations one and the number of subsets. So yeah, harder problems, you might get uglier answers. And I guess that's sort of the first part of this. So I'm going to move on to something called the generating function. You guys seen this before?
I have.
Okay, 1. Fantastic. Okay. So there's a sequence, which I'm sure you're all friends with. Powers of 2. Okay, so what is a way? So generating functions are just a way of sticking sequences of numbers together in a nice, useful way. So what we're going to do is we're going to call this function g of x. It's 1 plus 2 times x plus 4 squared 8 x cubed. And so on, right? We can, all we're doing here is attaching numbers as coefficients behind series. Okay? We've done absolutely nothing interesting yet, we're just explaining sort of this notion of generating functions. Okay, and you'll probably all notice this is a geometric series. And it's equal to 1 over 1 minus 2 to the x. Okay, now this is just the formal way of sticking numbers in. And this here kind of becomes a shorthand. Okay, everyone happy? Now when you do combinatorics, they keep saying this is just a shorthand, you know, and so on. And then we kind of stick up in the scenarios and do regular manipulations, which are justified anyway. But heads up, that's what we do. Okay, so great. That is a generating function, and that's what they look like. And the nice thing, of course, is that you can then find out the nth term from the generating function, if you ask very nice sometimes. Okay, so here's another sequence which I think some of you might know. 13, 21, 34, and so on. What are these called?
Random numbers.
Yes, they are called random numbers. That is correct, Jen. And yes, it is on the shirt, Joel. So these are the Fibonacci numbers. So shall we talk about the generating function?
Yes.
Yeah, we're going to. Okay, so f of x is equal to 1 plus, I'm going to say 1 times x plus 2x squared, 3x cubed, 5x to the 4. Yeah. You guys get that. So, does everyone see the nice, obvious way to sum that up?
No.
Okay, no. Okay, so turns out there's not really one, but there is a clever, non-obvious way to do it. Let's multiply by x. Okay, that's what you do with things, right? Okay, I'm going to sign up something at x to the 7, and I'm also going to multiply it by x squared. Okay. Well, now does everyone see what we do? Anyone have any ideas? Okay, dogs are better than cats. Wow, no reaction at all. Okay, guys. Okay, anyone have any ideas? Yeah, we're going to subtract. So subtract on this side. This thing minus this gives us 1.
Yes.
Yeah. So f of x, what's f of x? This generating function of Fibonacci numbers. Okay, so we get the generating function. Okay, that's good. Now the nice thing here was this we know how to turn into a geometric series and get the nth number, right? We don't really know how to do it here. Do we? I mean, we can try write this as a power series, but what will happen then is we'll get 1 over 1 minus, and this is right. We can do that. But that's not really going to tell us the coefficient of like x to the 50. It's in a whole lot of terms, we have to add things. Right? That's going to suck. So we use some nice magic called partial fractions. Have you seen partial fractions? Okay, hands up if you have not seen partial fractions. Okay, hands up if you have seen it. Okay, and the rest. Okay, so most of you actually had hands that time. That's good. I suppose I should just go over it. But the idea is that we'll have a rational function. Something like x plus something like that. Okay? So the first thing we'll do is we'll just divide out the top part, because we do not need to deal with this. The numerator can be higher, can be lower than the denominator. In fact, that's too nice. Constructing a nice example. Sorry. Minus x. Yeah, let's do that. Okay, well, this is equal to, if I got this right, okay, so those two are x times that. That's x cubed minus x plus 1 that's x plus 1. Okay, and yes, I am skitting over doing anything too horrible algebraically, but you can do this. This thing is very nice in that it's got two roots, 1 and minus 1. So we're going to kind of run it like this. Okay. And all that's going on here, A and B are constants which we have to find. Okay, this is the step you need to do. And well, we're going from here to here. So we'll have a times x minus 1. Okay, that's the denominator, that's the numerator when you multiply things. Here's 2. Okay, and that's going to be a plus b times x plus b minus a. Okay, a plus b is 0. B minus a is 2, b is 1, a is minus 1. Okay? So okay. So you do this and you split it up. And the first thing you should be asking yourself is, well, who cares? Maybe that's not the first thing you should ask yourself, but okay, what does that help? So here, it's just a way to get into a different format. Sometimes you factorize a polynomial because it's more convenient. Sometimes you multiply things out because it's more convenient, right? In this case, these things are convenient because we can turn them into geometric series. Yeah, not these, but the roots of this part of this quadratic, right? Okay. Okay, so right, we have this Fibonacci generating function. Okay, now does this polynomial remind anyone of anything? Yes, the golden ratio. I assume that for a lot of you I'm sort of talking old hat, but yeah, it's the polynomial which gives us the golden ratio. Okay. Do I need to explain the golden ratio? Has everyone seen it? Has anyone not seen the golden ratio? Oh, okay. Yes. Okay. So the golden ratio, you have a rectangle, and side length 1 and the other side length will be the golden ratio. You cut off a square at the bottom. Okay, 1 by 1 square. And this rectangle will be the same size. That's the definition of the golden ratio. So what does this mean? It means that 1 over phi is equal to phi minus 1. Multiplying everything by phi, we get 1 is phi squared minus phi. And really that's all that happens. Okay? Now there are two roots to this polynomial, same as the two roots to that polynomial. And they're 1 plus minus root 5 over 2. Okay, just from the quadratic formula. Yeah. So the golden ratio is like 1.618 something. And its evil opposite is like minus 0.618 or something. Okay? So, using the magic of partial fractions, and I am this time not going to go through the horrendous evil and pain of computing A and B. I'm just going to write down things. It's 5 root 5 minus the golden ratio x. Okay. Now this thing is a geometric series, right? It's the summation of a geometric series. Really anything that's of the form a over 1 minus bx, we can expand into a geometric series, right? It's equal to yes? Okay, cool. This is a geometric series. And so is this guy. Okay, so what's this? 5 root 5 times 1 minus phi x plus phi, plus phi x plus phi squared x squared, phi cubed, so on. Right? That's a geometric series. Plus 1 over 5 minus 1 over 5x squared. 1 over 5 is 1 over 5 is 0.618. It's not, not the negative. There's a little bit of that detail I'm skipping over here. That's a minus. Dot. Okay, now what is the coefficient of x to the n? Yeah. Well, x to the n only appears in two places. Okay, so well, firstly, the coefficient of x to the n is the nth Fibonacci number, right? definitions. Okay, but it also appears in two places here. It's phi over root 5 times phi to the n. Oh, and there's also a term coming from here, which is 1 over phi root 5 is 1 over phi to the n. Well, to the n. Okay? And this gives us an exact formula for the nth Fibonacci number, which follows from the recurrence. Okay, now, is this any nicer than the recurrence? Well, if you want the millionth term, it can be. Now, I'm going to do a little bit of magic and write and instead of writing phi, I'm going to write like a 1.618. Okay, so this is like 1.618. Okay, root 5. 8 to the n. Okay, that's the geometric term. Okay, we've just written the Fibonacci numbers as the sum of two geometrics. Okay, plus 1 over 1.618. And this, well, 1 is 0.618 to the n. This term is going to vanish. Right? Like this is just going to get small. So most of what we care about is this. Okay, that gives us a nice approximation for the Fibonacci number. Fibonacci numbers grow roughly geometrically. I'm sure you've all seen that before, right? Okay, but what we've added here, which is really nice, is Fibonacci numbers grow. Fibonacci's grow exponentially in this way, but so does anything that comes from a linear occurrence. Now, maybe let me be a little bit more exact with that. Okay, imagine I write an is 4a minus 1 plus 3a minus 2. What part of the analysis I just did breaks or changes? Well, more or less nothing, right? I'm going to have the... well, should we do this example first? Okay, yeah, I'm going to generalize a lot. So, okay, so we have a0 plus a1x plus 2x squared plus dot dot dot. I'll call this ax, right? X, ax, a0 x, 4, looks like that. Or a1 x squared plus dot dot dot. 3x squared ax dot dot dot. And what we're going to get is ax times is equal to a0 plus a1 minus 4a0 x, and we'll get an exact formula for this. Okay, cool. We've got an exact formula now. Okay, and then we can break up this polynomial into its roots and expand and do partial fractions, and all of that stuff kind of goes exactly the same way. By kind of, I mean goes exactly the same way. Really, I can even go an is b. Okay, where b's where A is still a sequence and the B's are just constants. And we can multiply across and you'll get a divisor of 1 minus b1x. Dot dot dot. Okay, just okay. And I'm just going to run a polynomial. Okay, and then once again, you can apply partial fractions and write all these terms as sums of geometric series. So time. Okay, good. Okay. Sorry?
How will we apply this?
Well, if you come across a question which is asking you for to find the nth term of a sequence, this is a hell of a good way to do it. I believe question 1 in the PAMA last year, you could literally solve by applying this. Is that what you took? Yeah? Yeah.
To get it generated.
Well, so the generating functions are used to find the nth term of a series, which is given by a recurrence. So if you give me a recurrence, I can find the generating function. I can take the generating function, I can split it into a bunch of geometrics, and I can find the nth term. Now, that's quite a powerful general tool. Okay, if you've seen this in the PAMA in last year, if you know this stuff, and you got that PAMA question, you could literally apply it and you'll be done. Now, that was quite a nice series, so you might have done better by just look for a pattern and apply it. But yeah, you can throw this at it and you will be done in no time. So I think I'm going to So a particularly nice case of this, the Fibonacci numbers. Fibonacci. So you start with 3 ones, and then you add up the last 3. 3, 5, 9, 17, so on. These will grow, and they'll grow like the largest root of 1 minus x squared minus x cubed. It's like 1.8 something. And if you go to the Fibonacci, it's 1 minus x squared minus x cubed minus x to the 4. Okay, and so on. And these get closer and closer to 2. And the reason they do that is if I let this go off to infinity, there'd be a root and a half, and okay. I'm going to just talk about something else called the Catalan numbers. So Catalan numbers count a whole lot of things. Richard Stanley, in book 2 of the series, he literally has an exercise which says, here are 66 definitions of the Catalan numbers, and you should prove they're all equivalent by finding bijections between the kinds of things that they're counting. And if you go to his website, that list has increased from 66 to, I think, 300 and something. Yeah, someone had a lot of time for that. And I don't think that you're actually expected to find direct bijections between every pair of them. I really hope not, at least. Okay, so anyway, I am going to talk about a thing called a particular definition, which is popular, called Dyke path or Dyke path. Okay, so I've never gotten a consensus, or rather I've gotten consensus both ways on whether that's pronounced dyke path or dick path. Either way it sounds dirty. I'm sorry. I promise you I did not make this up. So, this is a path of length 2n. Made up of diagonally up and diagonally down steps. Okay, n of each. I'm just going to draw one. Okay, so up, down, up. Okay, so what are the rules about dyke paths? Well, they can't go below the origin, and they have to end up on the line. Those are the two. Okay, everyone clear on those? Question is, how many are there of length n? And by length n I mean of length 2n steps. Okay, so can I write here? Yeah. Okay, well, D1 is string 1, right? D2, well, you can either go up twice and down twice, or up, down. 2, D3 starts to get a little ugly, right? Yes, no, maybe. Okay, well, fortunately, we can find a recurrence for the Catalan numbers. Okay, so how many paths are there length n? Well, one thing you can do is you can go up. You can never go below this line, never touch down again, and then do that. So that's dn minus 1. Plus, maybe you do go up and crash for the first time at position k, right? Okay, so it's at position k for the first time. So the k minus 1 paths, well, the dk minus 1 paths there, and then you do something to that. And that's the sum cross k, ck minus 1, cn minus k. Okay, now, what we've been playing with today are once again these generating functions. So what I'm going to do is I wanted to call them Catalan numbers, and then I changed it to dyke paths, and we'll go on with D. I'm going to shove a D to the n on them. Okay, and really I can think of this as D0 as 1, because it's convenient. So this is just a sum across k of k minus 1, k minus k. Okay, sum across k minus 1. Let's do that. Okay. Anyone have any ideas where this is going? Well, let's split this up. That's x times tk minus 1. Okay, and the key insight is that this stuff looks a whole lot like a function squared. So summing across n now, we get dx is 1 plus x d squared x. Okay, so now this is important. This gives us a nice functional equation. You guys like functional equations, right?
Yeah.
Cool. This gives us an equation for d. And hey, it's a quadratic. And it tells us that d of x is this. Okay? And this is how, this tool lets us actually compute the nth Catalan number. Okay, generating functions are powerful. And it turns out the formula for dn, yes?
How do you know that it wasn't 1 plus 8
That is a very good question. So for 2 plus, you run into it's a good answer to this. I'm trying to remember it. I think it's either that you run into negative numbers very quickly when you try it, or that you have some kind of derivative condition, and Olympiads don't teach derivatives, so we're just going to gloss over that. Yeah, that's the idea. Okay, now that works out being the formula. How do I get from this to this? Evil algebra. Who's coaching algebra this year? Yeah? Yeah, evil algebra. He's as likely to say that as anyone else. Okay, cool. So now what is 2n choose n? Well, it's the number of these paths that don't that end over there, but maybe could drop below the axis, right? Yes? So you have a path, and it goes up and down and eventually lands back at the center. And it's of length 2n, or length n, depending on how you want to look at it. And the probability that it ever goes below, or that it stays above the axis the whole time, is this nice 1 over n plus 1 fraction. Well, that's quite nice, isn't it? So let's prove it. And let's not use generating functions because we've already used those. Really what I mean to say is we've proven that with algebra, but there is a much nicer proof, which comes to this. So imagine that you have this path. Here's 0. And then imagine you don't constrain it. Imagine you say, well, it's okay, maybe you go below the line. Right? Here's the first time you go below the line. You hit -1. I'm just going to reflect everything else. Everything after that, right? That's allowed. And I'm going to get all paths that end up, at -1 over here. Right? How many paths like that are there? And yes, you can prove that you get everything, and you can prove that you don't ever have, that you don't get anything twice. Well, that's 2n choose n plus 1. Okay? Turns out that 2n choose n minus 2n choose n plus 1. I'm sure you guys can all do this. 2n factorial, n factorial, factorial is, well, we have to put them all over the same thing. So let's make it this one, factorial, multiply that one by n plus 1. And this one I have to multiply by n, but it's still 2n factorial. So 2n factorial over n factorial n plus 1 factorial, which is 1 over n plus 1 to n. Okay, and yeah, that's what I wanted to get through today. Any questions at all? Oh, right on time. Yeah, like literally as you came in. Yeah, over to you. Cheers, guys.